Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hi folks, welcome to our Automotive Risk Assessment webinar today. I will talk about experiences from a lot of performed TARAs in different roles for OEM, Tier 1, etc. I will talk about observations, experiences, and of course lessons learned. At the end, I will give an outlook of what could be the next step, but this will be mentioned later. First of all, I would like to introduce myself briefly. I'm working since 2017 as a principal consultant for Kugler Mark. My main topics are cybersecurity, functional safety, ASPICE, and privacy. I'm an auditor for management systems, especially for information management systems like TSAX or ISMS according to the 27001. I'm member of the committees of a mirror group of the VDA Cybersecurity DIN AK, which is defining the 2034 or the 5112. I'm leading an automotive cybersecurity group at ZVEE, and I'm member of advisory board Intax, leading the working group of cybersecurity SPICE at Intax. Kugler Mark is working mainly for the automotive industry, for the topics of functional safety, cybersecurity, automotive SPICE, HR, and in general for every process improvement. Please have a look on the content. I will talk about in general about the risk assessment methods, especially the threat analysis and risk assessment as defined in clause 15 of the ISO SAE 21434. Next, I will show you some examples of what we have seen performing TARAs on customer side. I will summarize observations, hints, pitfalls, lessons learned in highlights of our findings. At the end, I will talk briefly about an outlook, especially the combination perhaps of cybersecurity and functional safety of what you can think for the future. Let's start to have a look, a deep dive in the risk assessment methods. The risk assessment method is defined generally in clause 15 of the ISO SAE 21434. It is about 7 steps. It can be invoked from different points in the life cycle. The first step is the asset identification. It's capturing itself 3 sub-steps. It's about asset enumeration, allocation to the cybersecurity properties, and defining the damage scenarios. As a second step, you can think about the threat scenarios related to your damage scenario you have defined the step before. The impact rating will rate the severity of the damage scenario. The fourth step will be the attack path analysis. That means you know the threats, you know the damage, and now you have to think about how you can elaborate on the threats. How can you realize the threat in order to cause the damage? The next step will be the AirTag feasibility rating. That means you have to think about how easy it is to perform the AirTag you have analyzed before. The next step is to determine the risk value. It's a combination about the impact rating and the AirTag feasibility. At the end, it's the definition of a cybersecurity risk within the standard. At the end, the seventh step is about risk treatment decisions. You have 4 options and you have to define and you have to choose one of the 4 options. The next slide is showing how you can invoke the risk assessment within the concept phase. You have to start the concept phase with an item definition. If you don't know the item, you cannot perform a risk assessment. That's for granted. You have to identify about the cybersecurity goals. You need the cybersecurity goals to define later on cybersecurity requirements. In order to be able to derive cybersecurity controls and requirements, first step, you have to identify the risks, you have to define cybersecurity goals. Therefore, you are invoking the risk assessment, clause 15, after defining the item. As I said before in the slide, you have 4 options at the end. If you know the risk, you can accept the risk, you can avoid the risk, you can reduce the risk, or you have to transfer the risk. This is the risk treatment decision. If you know the risk treatment decision, the next step would be either to define a cybersecurity goal in order to have to reduce the risk, or you have to specify a cybersecurity claim if you want to accept, avoid, or transfer a risk. The last step of a concept phase is then to allocate your cybersecurity controls and your cybersecurity requirements derived to achieve the cybersecurity goal to architectural elements. This hidden object picture is showing our 9 to 5 TARA navigator. That means the 9 steps in order to retrieve 5 objectives. The description of performing a TARA in the security standard is high level. It describes the what rather than the how. There's a lot of room for interpretation and selection of the most efficient methods. And therefore, we highlight for the different steps special information you can take into account in order to perform your TARA effectively and efficient. Several additional information sources and methods and guidelines must be used for an efficient implementation. If you are in a safety project, then of course you can use the HARA as an additional input in order to make your TARA and HARA consistent. This we will see later on. Just to take out some examples, you see the UNICE is providing some catalogs, for instance Annex 5 threat catalog. You can use ENISA, we have a taxonomy of assets you can take into account, or the MS-DRIVE method in order to get your threat directly out of your cybersecurity properties. You can perform attack tree analysis, you can use the METRA databases as a list of vulnerabilities you have to consider. You can have a look into the ISO 26262 if you need the S value for your TARA to define the safety impact of your damage. So there are a lot of additional information, guidelines and papers you have to use in order to perform your TARA. This was very briefly an overview about the TARA, about the risk assessment method as it is defined in the 2034. Now I will come to the point where I will talk about the examples and the experiences we have made if we perform a TARA in real life or in real customer projects. First of all, what we see is that we have to decide about the level where we want to start the risk assessment. The standard is showing you how to perform a risk assessment if you are in a concept phase, that we have seen some slides before. But in principle, a lot of suppliers, tier 1, tier 2, etc., are not starting in a concept phase, but they have a contract to develop a piece of software, a piece of hardware, an ECU, a special function, or anything else. In this case, they are not able to perform a TARA on a high level, on a top level, on the item level of a vehicle. But of course, they have to identify cybersecurity risks. They have to think about cybersecurity controls to be implemented, and they have to think about cybersecurity requirements. They have to verify at the end in order to achieve the cybersecurity goals. So what we see is that you can perform a TARA on different levels. We have an example here. You have, for instance, the top level, the asset, the ADA steering command received by a steering ECU. That can be a function on a high level. A cybersecurity goal on that level could be prevent unintended steering through malicious steering command. That's on the vehicle level, top level. On the next level, system design, you have to think about what are my system requirements. For instance, steering command shall be authenticated. Non-repudiation of steering command shall be ensured by logging of received steering commands. That could be a requirement derived of the cybersecurity goals on system level. Now you have to implement the cybersecurity system requirements on hardware and software level. So you have to think about the next level, and of course you can perform a risk assessment on software level as well. You can derive cybersecurity controls. You can derive cybersecurity requirements on software level. For instance, software requirement use the CSMM MAC verify functions on the CSM. This is only one example, and what we see is that different suppliers, different tiers are working on different levels. At the end, of course, the TARAs should fit together. That can be hard to perform because it's not all in one hand, and perhaps the OEM do not want to provide the complete TARA to his supplier. Let's have a look on a specific example, our training example, the anti-theft device. It's a function on vehicle level, moving the seat in front of a steering wheel so that you cannot steal a car anymore. You see the components which are relevant to a function, the external connections, the external components, and the interfaces in between the different components. For instance, the interface component of the OBD. Like a burglar who is coming from interface to your house, that means windows or doors, an attacker is having a look on the interfaces of your component in order to have a way to the target, to the asset, to the crown jewels. There are different ways normally, and typically you have to identify all the ways through your risk assessment. For instance, there can be one attack path coming from the outside, car to X communication, and via the antenna through the telematics ECU to gateway server, body controller, to the ECU seat manager, and then he is in the position to tamper, for instance, the motor, to tamper some data here. This is one attack path you can think about if it is feasible or not, which can be taken by an attacker. Another path could be via the OBD interface, via an OBD dongle for instance, via the bus connector to the body controller to the seat manager memory. Another path could be that you try to tamper the angel sensor to the seat. This is showing only 3 possible attack paths you have to identify, and you have to analyze through your risk assessment, and later on you have to determine the attack feasibility in order to get the information if you have to define cybersecurity goals, cybersecurity controls to avoid that the attack path can be exploited later on by an attacker. In most of the cases, we have seen that the MS-TRIED threat modeling was applied. It's a systematic way to derive potential threats which can be applied by attackers if you know the cybersecurity property which will be compromised. As a first cybersecurity property, you can use authentication, that means proving the identification of something. Integrity means there is no manipulation of data possible, all the integrity is kept. Non-repudiation, there are two things. The first one is that you can not repudiate if something happened, and the second thing that replay attacks are not possible. Confidentiality means there is no unauthorized disclosure of information. Availability simply means that a function, a service, even a software is available if you need it. Authorization means if there is a rule concept behind, then it's not possible to elevate the privileges. The standard is asking you for using three cybersecurity properties, the classic CIA scheme: confidentiality, integrity, and availability. The Stride threat modeling is proposing that you add the three cybersecurity properties in order to have a one-by-one mapping to the possible Stride threats. First one, spoofing. Spoofing, for instance, means the attacker pretends to be someone or something else. He can tamper his identity. Tampering means that there's no possibility to tamper data in flow or in rest. Repudiation means attackers perform actions that cannot be traced back to them. And information disclosure simply means that you can provide some information which should be not disclosed unauthorized. Denial of service means the service function or whatever you are investigating is not available. And elevation of privilege means that somebody can do things which he is not allowed to without elevation of privilege. Not for any kind of asset it makes sense to allocate each cybersecurity property possible. You see the table for different kind of assets, for instance, external entity, the process, the data flow, and the data stored, the possible cybersecurity properties which could make sense. For instance, for a data flow, the integrity is possible, the confidentiality is important, the availability, the classical CIA are relevant for data in flow, that the data will be not tampered, will be not disclosed unauthorizedly, and the availability of the communication is provided. For an external entity, for instance, it's important to know the authenticity. Who is providing some information to another ECU? Non-repudiation, the same one. You want to know, you want to prove what happened in your system. That means if you have the selection of the asset, the kind of actions, then it's very easy to have a look on the cybersecurity properties which makes sense to further being investigated. So that means you don't have to allocate every cybersecurity property to every asset in a mandatory way. You can select which cybersecurity properties are making sense. You see the examples of the kinds of assets, like external entity could be people, other systems, processes could be a DLL, an exe, a component, a service. The data flow can be a function call, can be a network traffic, or the data store is where you can store data, database, file, shared memories, etc. As a last point, you need a trust boundary. That means, can you trust the other sender, for instance? Is there a boundary in between? Let's take an example. A user wants to get knowledge about a data in the system. Therefore, he is performing an OBD data request to the system, and the system is asking the memory for the data, providing back to the user. You cannot just trust the user, and therefore you see it's a different trust boundary between the user and the system. On the right side, you see the proposal of the Stride threat modeling about the cybersecurity properties to be considered. Let's take an example. Evaluating the data flow, the STRIDE model is proposing to investigate the cybersecurity property, integrity, confidentiality, and availability if they can be compromised. The held errors are showing to the data flow diagram to the interfaces where the data is coming through. So in between the user and the diagnostic ECU, or the diagnostic ECU and the memory. You cannot just trust the user, and therefore you see the trust boundary between the user and the system. Once you have investigated the cybersecurity property relevancy, you can simply retrieve the threats. For instance, for integrity, tampering is the threat. That means tamper the OBD responsive can be an identified threat, or block the OBD request to the diagnostic ECU can be a threat for availabilities compromising. Based on what I've explained so far through the last slides, I hope you got an impression about a risk assessment or TARA is about and what are some main components of a method. Now in the next part I would like to talk about the highlights of what we have seen specifically, what we have learned, where we saw some pitfalls, and this is what I want to summarize in lessons learned of the next part. If we start a TARA, the biggest challenge is to come to a common view on the architectural design. This is not very easy, even it sounds easy. What we see in a lot of cases is that the team, if we call the team together for the first time starting the TARA, the first workshop, that there is no common architectural design and not all of the participants do have the same view on the architecture. So we have a lot of discussions about the architecture at the very first point before we can start the TARA. We have to think about the starting architectural design. Is it a component diagram, for instance? It's more related to a component-based risk assessment. Or do we have already data flow diagrams that make it easier to perform, like we saw in the STRIDE model, like we perform a function-oriented or a data flow-oriented risk assessment. Often we observe a lack of information about interfaces, trust boundaries, and about the operational environment. All of them are very important for performing risk assessment, and therefore it's crucial to have them all on board if we want to start the TARA. Second questions to be answered at the very beginning of a TARA is the level of abstraction to start a risk assessment. It's not always clear the level, and the standard is giving no guidance except that they saying during the concept phase you have to invoke a risk assessment method, the TARA, the clause 15. But how can you start if you want to perform a risk assessment for software, for hardware, for an ECU? It's not explained. And it's a very crucial thing to define at the very beginning the abstraction level. If you want to start with a component diagram and you have 20 components, or you want to start a functional oriented risk assessment with 100 functions, you will not be able to get ready. The complexity and the effort will explode. And therefore it's a very crucial thing at the very beginning to define what is the level you want to start your TARA. Another subject we see at the very beginning of a TARA is that people and the teams are talking about pre-filtering of assets, damages or threats. This is very dangerous because risk may be overlooked if you are filtering at the very beginning already some kinds of damages or threats. So you have to be very sure that it is in a correct manner done and you will not overlook some risks. For instance, discard low impact, low severity damage scenarios. When you say the damage is not that big, the severity is very low, therefore we will not consider them in our TARA. Another thing is discard threat attack paths with low feasibility, low attack feasibility. You can say, okay, the attack feasibility is such as low that we will not consider it as a risk. For instance, possible focus only on remote attacks, that you say only remote attacks are of interest, or vice versa, only attacks via the OBD is of interest. You can do that, and even the standard is giving you some possibilities with its permissions and recommendation, but think of it if it is not too dangerous. For instance, the example in the standard is if there is a low impact on safety, you do not have to proceed the assessment for the other impact categories. Could be that it makes sense in that case, but what is in the other case where the financial impact is very low? I think you have to continue investigating the risk because there could be a safety impact and you cannot just decrease the safety impact without evaluating it further. Coming to the second list of our highlights. First point, take care about assumption. Whenever you do a justification that you say the attack will be not possible there, the damage will be not as severe due to or whatever, then you have to be sure that your assumption you are taking into account are correct. In several cases what we have seen is there is some assumption that another supplier or customer will take care about the risk. This you have to prove at the end, you have to validate. And therefore, take care if the assumption is really correct. Second, it's good to consider predefined catalogs for threats, for cybersecurity controls and measures, for assets, etc. There are already mandatory catalogs to be considered as a prerequisite for the UNICE homologation, like for instance the UNICE Annex 5. But also don't solely rely on it as it is grossly incomplete. That means you cannot have one catalog and then this is for all the risk assessment you will perform in the future. The third bullet of this slide is a very important one. You have to perform a risk assessment as a team activity. It cannot be done by one poor cybersecurity guy to create and define the complete TARA. You have to involve necessary stakeholders like system architects, software, hardware expert, tester, skilled attacker, cybersecurity and safety experts. But of course, which will increase the effort you need. If you have a big team and they will meet on a frequent basis through several weeks and months, it is a cost factor. Often one or a few people in a single group create TARAs. This is what we saw, but this should be not a regular case. What we saw in addition is the involvement of tester and skilled attackers is rare in development phase due to missing effort. They simply don't have any time to develop a TARA. Finally, modeling and assessing is useful for the design, but it cannot guarantee a secure implementation. Think about your catalogs. They are useful that you don't have to start by zero for each TARA, but of course the catalogs will be not stable over the time. There can be some changes, there can be some attacks in addition which are known through the time. What experiences did we make? The TARA helps as an analysis method to identify open points, but often rather confirms the controls that one has already planned to implement. That means the teams always do have some cybersecurity controls, measures and requirements in mind. If they have to use the HSM, for instance, if they want to use encryptions, etc. The decision is made before, so therefore the TARA is mainly to prove that this is a correct decision done before and nothing is missing on top. This is what we see in a lot of cases, that the TARA is supporting the decisions which were made already. A gap in the standard from my point of view is that there's no requirement to reiterate the TARA once you have done the TARA and you have decided about the cybersecurity controls. It is not prescribing any iteration or even evaluation of the effectiveness of the controls you have decided to implement. This is part of the other standards in other domains, but not for the automotive so far. So this makes it difficult to assess the acceptability of a residual risk, because there is no strong requirement to perform such kind of assessment, and you are free to implement your controls. Up to now, there is no CAL mandatorily in place, and there are no method tables in place describing the strengthness of the development of the cybersecurity controls and requirements you want to implement. Another subject not defined precisely by the current standard is that for the evaluation of risk value, existing measures for possible risk reduction are not taken into account. Take the example you are in a safety project. Perhaps there are already defined a lot of safety measures that makes impossible to perform an attack where the attack feasibility is high from a cybersecurity point of view. But if you have a look into detail, then perhaps several safety measures can be avoided to perform the attack. Our recommendation is, if you have specified the cybersecurity goal, decided on the cybersecurity control, you should interact with the safety expert if it makes sense and there's no contradictory measures in place from cybersecurity and safety, or even safety measures can support the cybersecurity goals, and perhaps in the best case you do not need any additional cybersecurity controls because the safety measures are already strong enough. On the fourth point, the complexity for sub-threat models increases dramatically. Think, for instance, about different operational states like secure boot, driving, etc. You have to investigate if your cybersecurity property cannot be compromised depending on the operational state you are within. Therefore, you have to investigate per line the asset, the damage scenario, your cybersecurity property per operational state. And then you can imagine that it could explode if you have a lot of different operational state, a lot of cybersecurity properties, etc., etc. After refinement of the sub-threat models, the TARA is refined. Let's have a look on another example. I hope it's simple enough that it can be easily understood. When transferring an attack path to a system architecture, this results in a single flow impact chain, effect chain, sequence data flow. And this example includes numbers which display the sequence. This shows a typical function chain where different cybersecurity controls are integrated. The example above is a simplified picture of a steering command by a park assistant ECU. Only at a specific speed lower than PKL parking mode limit, and in case of an authenticated steering command from a parking assist ECU, the steering request shall be accepted. The picture shows the cybersecurity controls integrated. They are derived along the attack path of a threat scenario. Number 1. The code block of a software in the ROM is signed with a key. No unauthorized code change has happened. Number 2 is showing authentication of a messages steering request speed by SecOC, that means the secure onboard communication, and MAC, the message authentication code. Number 3, the library SecOC using the CSM, that means the Crypto Service Manager, MAC verify function to check the message authenticity. Number 4, on RTE a fault flag is set if MacVerify is failing. Number 5. The parking mode limit is secured by a hash key in order to secure the data integrity. Finally, number 6 and 7. Before a steering command is further interpreted for whitelisting strategy of functions, a validation station drive mode function checks the state of a system, speed lower than parking mode limit, speed authentication was okay, steering torque request message authentication is okay, etc. and offer calls the basic power assist steer function of the steering control unit. For every session, you usually find a refined architectural threat model and counteraction, that means cybersecurity control. In this picture, you find a simplified picture of a secure boot session. We will go through quickly and in the same manner as in the example before. 1. The code block of a bootloader has a signature. The digital signature is a mathematical scheme for verifying that the bootloader has not been changed. For a bootloader, a special key called bootMAC key is used and stored in the secure HSM memory. The activation shall only be possible by an authorized digital on and clamp 15 is high on, ignition on. The validate session boot mode reads the bootMAC key uses the bootMAC key to check the signature of a code block. Finally, if the signature is correct, the bootloader will be executed. Otherwise, the session will stop with no booting. Usually, the analysis starts with a software state machine and then drawing a threat model per state and connects the models. See therefore a typical example. Per state, a threat model is drawn. Per state, the signal flows and interfaces are analyzed, and interfaces which can carry an attack are marked. Also, the transfer from one to the next state is secured by security controls. For instance, operating flags are checked. Let's start with a collection of our observations. Risk assessment are divided into different risk assessment, starting with a component-based risk assessment. This is what we saw mostly. We found both. On the one side, component-based risk assessment or function-oriented risk assessment. The component-based oriented risk assessment are normally easier to perform and to comprehend. Single cybersecurity assets and their compromise are much easier to isolate and assess because you are concentrating only on a specific component. Cybersecurity properties can be more easily understood and attacks of them considered. The impact of an attack is easier to describe and evaluate, and the attack surface normally is limited via the interfaces of your component. The difficulty for this approach remains to map at the end the component properties to the criticality of a function, because at the end, of course, you want to ensure that the functions are performed in a secure manner as specified. Several teams want to start with a function-based approach because, as I said before, we have to ensure that the function will perform in a specified secure manner. But functions as assets are not easy to analyze due to potentially long and complex attack paths. In a worst case, the function is going through a complete architecture to all the components. Functions usually span multiple interfaces through multiple components and thus define a large attack surface. The number of attacks can increase, as can the ease with which an attack can be carried out. And nevertheless, this is a frequently observed phenomenon. Second part of the observation, challenges. Assets are always difficult to analyze, for instance, if safety targets, safety mechanisms are there as well. In combination, there's a very complex environment and a very large attack surface. So from our experience point of view, the implementation of TARA show that they are usually not considered in the beginning and perhaps are gradually added when further information of a project can be used. Because otherwise the complexity to the starting point is very high. Another challenge is if you allocate cybersecurity controls to the organization. You want to transfer the implementation and achievement of a cybersecurity goal to an organizational measure or control. Of course, it has to be known on organizational level and it has to be ensured that it can be validated at the end of development so that you can ensure that your organizational measure is really taken. Good knowledge of one's own cybersecurity management system greatly facilitates the analysis. If you don't know your cybersecurity management system and you don't have any clue about the measures already implemented there, you are not able to allocate cybersecurity controls on your organization during performing the TARA. As we saw by our simple example, the different levels and the combination of a different level makes the TARA complex. So at the beginning of a project, perhaps you even do not have enough details to consider all relevant information. For instance, you will not have a data flow diagram of your software or your hardware, so that you have to wait till you can perform a breakdown within your project. Whoever was performing attack trees to create attack paths knows that it is not an easy task. Use attack trees for evaluating the feasibility of attack paths with special cases carefully, otherwise you will be bogged down into minutiae that isn't helpful. Last slide of observations, lessons learned or recommendations. First one, focus on remotely controlled attack types. These automatically lead to higher risk values when the attack vector approach is used to determine attack feasibility. But different situation for remote attacks without code insertion and execution. This is part of a remote attack, perhaps. Second, a question about social engineering attacks. Do you have to capture them in the TARAs? These types of attacks are frequently difficult to classify, and often the countermeasures are defined via organizational rules within the cybersecurity management system, like awareness of the employees, awareness of the teammates, or rules that you have to handle information due to the classification and handling matrix of your information security management system. So in a lot of cases, we saw that the social engineering attacks are not part and not handled via the TARA. Another recommendation is to tailor the attributes used to assess the attack feasibility to your needs. Some attributes proposed by the standard are difficult to assess and cannot be evaluated unambitiously, especially if you are tier 2 or tier 3, for example, and you don't know exactly the use case for the functions. Some attributes frequently used for practical reasons are currently not considered, especially the attacker motivation, the potential benefits, attack scalability, etc. At the beginning, defining the 2034, within the ISO group it was discussed if the motivation of an attacker should be a parameter to determine the attack feasibility. In other standards like the 62443 or the common criteria, you can find such things. But at the end it was decided to not take this into account. Why? Because the rating is too difficult. For instance, is it a personal motivation by the attacker that then the attack will be imminent or not? how high a value of an asset has to be that an attacker will be motivated to exploit a vulnerability to perform the attack? Or is expertise and resources sufficient that the attack will happen? How can you rate this? This is an example we saw several times in some TARAs. When it becomes too easy, then it makes no sense to perform a TARA, because the result is not worthwhile the effort you have to put into TARA. The asset, for instance, is a software or another asset, doesn't matter. Cybersecurity property will be marked with integrity. The damage scenario will be specified as integrity will be violated, and the threat scenario will be defined as integrity will be threatened. The attack scenario then will be evaluated to attack to realize the threat scenario, and the cybersecurity goal at the end is specified as keep always integrity. This you have known before, so you don't have to perform a TARA in order to get such kind of cybersecurity goals. So that means the cybersecurity goal has to have much more specific. Of course, there's something about integrity if the cybersecurity property is already integrity, but think about how you can enrich these simple things in order to have a value at the end if you have finished the TARA. Last part of a webinar will be the potential combination about functional safety, so-called hazard analysis and risk assessment, and cybersecurity threat analysis and risk assessment. We saw several initiations about the combination, but from our point of view, this is not a common understanding. It's not a common usage of TARAs that always you have the combination if you are in a safety-related project. What we saw rarely in the past is the combination of HARA and TARA to gain one single risk assessment for functional safety and cybersecurity. From terminology point of view, you could compare, for instance, hazards with threats, ASIL versus cybersecurity assurance level, providing the strengthness of a development process, safety goals, security goals, safety mechanism with security controls, general methods to protect safety or security, safety requirements, security requirements, the functional safety concept and the technical safety concept. In security, we have one, the security concept. Several safety outputs you can use as an input for TARA, like safety goal or safety state. Both have to be protected from being attacked by an attacker to jeopardize functional safety as one possible impact of violation of cybersecurity. Therefore, we can use it as an asset to be protected. Rating potential safety impact compromising a cybersecurity property has to be done by the safety discipline. They are the expert for this, having correct procedures. It's not a discipline of cybersecurity. Causing an impact on functional safety by means of a cybersecurity attack can be an extremely attractive target for a potential attacker. Take the example of attacking a safe state. If you are able as an attacker to trigger a car into the safe state, you can raise up a denial of service attack. However, security targets are not easy cybersecurity assets to secure. Another way of thinking is that cybersecurity up to now is not a failure mode for functional safety and not part of product safety. You have to have a look about misuse versus abuse. Whether it is a systematic software error or a random hardware error from functional safety point of view, it can have the same effect of an attack. An intentionally caused impact of an attacker could in principle also have been caused by a safety failure mode. Its impact with severity should already have been assessed as such in HARA. If you are driving in the night through a country road and the lights are switched down, it's independent for you as a driver. It's caused by a random hardware error from functional safety point of view, or by purpose, by intention of an attacker who had access to your CAN bus and switched off the lights. Safety measures and mechanisms must be in line with specified cybersecurity controls without contradictions. Single events identified in a safety analysis that can trigger top-level events individually, in series or in combination, for instance minimum cut sets, can be exploited by attackers as part of an attack scenario of a possible attack path. Therefore, mutual consistency and completeness must be analyzed in the consideration. All, in brackets safety, single events must be analyzed as a security vulnerability. All known possible security vulnerabilities must be considered as single events in corresponding safety analysis. Safety output events, for instance coming from fault tree analysis, can also violate cybersecurity goals. Therefore, they have to be analyzed from cybersecurity point. At the end of the day, safety goals and cybersecurity goals must go hand in hand. This applies as well at the level of safety mechanism and security controls. Of course, they have to be consistent and they have to go in the same direction. The last point of the webinar, before coming to the summary, is talking about maintenance of TARAs. You have to be aware that a TARA is an ongoing document which will live for years. That means an initial TARA developed in a development has to be maintained after SOP. Much more frequently than in safety-related projects, the organizational measures must also be specified at the same time as technical measures. One of the most important requirements of UNICE Regulation 155 is to keep risk assessments up to date once they have been carried out. This is especially true for the post-development phases. They have to be understandable years from now on. Some positively impacting approaches from a field that we have seen are, for instance, defined methods, defined templates in advance, which are not trivial and not easy to create. We saw text patterns and justification in a well understandable form. Usability and efficiency in the implementation of risk assessment methods must be ensured. Another point important for the organization, especially for the CSMS, is to assign cross-organizational responsibilities as a procedural part of the CSMS or the Cybersecurity Operations Center. And this is for lifetime maintenance. Last point on the slide, definition, integration of an interface to the organizational risk management system to be able to assess subsequent changes in the cybersecurity posture and, if necessary, to react appropriately to them. This is part of the CSMS or the operational cybersecurity management to ensure. Coming to the silver bullets of a webinar, the summary. Good architectural design supports structural start. This is what we see frequently, that a lot of effort has to be spent up front, the real start of a TARA, to come to a good architectural design as a base for the risk assessment. It is good to consider predefined catalogs for threats and cybersecurity controls and measures, like for instance the UNICE Annex 5 for the threats or a NIST SP 800-53 for cybersecurity controls. The TARA does not prescribe any iteration regarding the evaluation of the effectiveness of intended cybersecurity controls. This is a weakness up to today. That means at the end you do not have to prove the effectiveness once again, like for our disciplines and our domains, our security standards do require today. Software service architecture can support the derivation of cybersecurity controls in a structured way. The breakdown of risk assessments into different levels, it's mandatory. So for systems, software and hardware, and at the end, of course, you have the challenge to combine everything to have a complete, consistent picture. Are you working in a safety-related project? Then, of course, safety measures and mechanisms must be in line with specified cybersecurity controls without contradictions. The safety standard 26262 is providing some examples for that. The combination of HARA and TARA is still under investigation. We saw several trials, we saw several studies, but up to now it's not the common usage of a risk assessment method for both in once. Consistency checks will lead to more completeness. Complete integration of safety and cybersecurity is not established so far. One use at the end of a webinar, the post-edition activities for the ISO SAE 21434 addresses current weaknesses of a risk assessment method, and there are several projects and further standards are created in order to come up with the weaknesses, for instance, with a clear definition of the attack feasibility, clear definition what does it mean, a cybersecurity assurance level, and so on. This slide bibliography is showing the list of references where I've taken out some information of the webinar. At the end of my presentation, I would like to thank you for your participation. Hopefully I've brought up some ideas and views you didn't were aware before that it was worthwhile for you to participate. In case of any questions, please contact me or my colleagues. I would be happy to get in touch with you personally. Thanks to the ASRG giving me the chance to present. Bye bye.